Before we start our discussion of Newton's second law, let's just go ahead and follow through a little bit on our last discussion. So once again, I've got my multimeter on my notepad. We talked about the idea of static versus kinetic friction. Now, when the mass of the multimeter is sitting flat on the table, the normal force equals the force of gravity. As we start to raise the incline, there comes a point where we overcome the static friction and the multimeter begins to move. So what just occurred? Well, our multimeter was sitting flat on the table, and as a result, the mass of the multimeter times the acceleration of gravity was opposed by the normal force in the equal and opposite direction. There was no net movement. As we began to increase angle theta here, what happened to all of these forces? Well, the static friction continued to act in that direction. And then we had two new components. This is our new normal force, and the vector of gravity was in that direction. So what was this force coming down, opposing the static friction? Well, as you recall, this was also angle theta. This force, which is equal to that force, is mass times gravity times the sine of theta. Now, initially, when the block was flat on the table, the force pulling it in this direction was 0. As a result, there was no net movement in this direction. But as we start to move the ramp up, we start to get a force moving in this direction equal to the mass of the object times the acceleration of gravity times the sine of this angle theta. And as angle theta became larger, this value became larger until it reached the point that it balanced the static friction. When we raised the angle a hair more, we were able to exceed this static force of friction, and the multimeter began to move. So once the mass times the gravity times the sine of this angle theta exceeded the static friction, what was the net acceleration as the block went down the ramp? Well, it was the mass times gravity times the sine of theta, which is this force right here, minus the kinetic friction. So in our previous example, if the static friction was 5, we could raise this angle until mass times gravity times the sine of angle theta also equaled 5. But once it exceeded 5, the kinetic friction pulling it back was only 3 newtons. So say that this value ended up equaling 5.1 newtons. And we said that the kinetic friction was only 3 newtons. So we subtract our 3 newtons, and our net acceleration equals 2.1 newtons. Does that allow us to determine the acceleration of the block as it comes down the ramp? As a matter of fact, it does. And with that, we'll begin our discussion of Newton's second law of motion. Now, Newton's second law of motion says that force equals mass times acceleration. So given the mass of the block and the force, we can determine what the resulting acceleration will be. Now, perhaps this would be a good time to introduce the concept of something called inertia. Inertia is the resistance of a mass to an applied force. And we can see what that does simply looking at Newton's second law. If we start off with a fixed amount of force and a known mass, we're going to get a particular acceleration. If we increase the mass of the object, what happens to this acceleration? Well, we're dividing the same force by a larger number, and as a result, acceleration will decrease. If we use a lighter object and apply the same force, we will get more acceleration. And that is how you can kind of mentally visualize the concept of what inertia is. The larger the mass, the less net acceleration from a given force. So you can take a certain amount of force and throw a golf ball with it, and the golf ball will have quite a bit of acceleration imparted upon it. You can take that same amount of force and try and push a car that's in neutral, and you will not get the same acceleration. It'll still move, but the acceleration will be much less. And in fact, it'll be less in proportion to the difference in the mass of a golf ball versus the mass of a car. Now let's take a look at our ramp again. So we raised the ramp to angle theta, which resulted in this vector of the force, which is the mass of the object times the acceleration of gravity times the sine of angle theta, exceeded the static friction force. And as you recall, we used 5.1 newtons pulling it down and a static friction force of 5 newtons. So we exceeded it and we broke it free. Now what we're dealing with is called the kinetic friction. And we're going to say the kinetic friction is 3 newtons going in the opposite direction to Fg. So what is our net force acting on this object? Our net force is going to be 2.1 newtons, and it's moving it in that direction. So what is the resulting acceleration in this direction of our object? Well, since force equals mass times acceleration, here's the force. If we divide it by the mass, we get our acceleration. Okay, so let's use an actual example. Say we have a 2 kilogram mass on a 30-degree incline. The force pulling it down the incline is going to be the gravitational force on this 2 kilogram mass, which is 2 times 9.8, times the sine of 30 degrees, which is 0.5. So we're going to have 9.8 newtons pulling this mass down, and I've got that listed right here. Now, if our static frictional forces were 5, we can tell that that has overcome the static friction and it's started moving. Well, now that we have movement, we're no longer dealing with static friction. We're dealing with kinetic friction. And the kinetic friction is less. We're going to say that it is 3 newtons in that direction. So our net force going down is going to be 9.8 minus 3 newtons because they're in opposite directions. So that's going to be 6.8 newtons divided by the mass of the object, which is 2 kilograms. And that's going to result in a 3 meter per second squared acceleration. Well, it's actually 3.4. Sorry about that. 3.4 meter per second squared acceleration, because we're dividing 6.8 by 2. Recall that newtons, what's the unit on a newton? So newtons are kilograms per meter per second squared. Now, we cancel out the kilograms and we end up with meters per second squared, and that's an acceleration. 3.4 meters per second squared is the acceleration. Now that we know the acceleration and the mass of the object, we can apply our kinematic equations and figure out its velocity. However, to do that, we're going to have to determine time and the distance that it slides down the ramp. So rather than give multiple examples, go ahead and start playing with this a little bit. Understand that force equals mass times acceleration, and use the material from the first video on the first law of motion to figure out what kind of acceleration you're going to be dealing with. And then give yourself some scenarios and try and figure out velocities given a distance that you determine. So you can say, for example, going down that ramp, you move a distance of 1 meter. What's the resulting velocity? So I'll let you have at that for a while. This is Bob the Science Guy. Thank you very much for stopping by. Make sure you give me a like and a subscribe, and I'll see you again soon. Take care.